Hello everyone, my name is Chong Huang. I'm from the University of California, Santa Barbara. Today I'm glad to introduce our work, Improve Active Speaker Detection based on Optical Flow. We start with the background. In this work, we focus on active speaker detection by fusing multimodal feature. Active speaker detection is to detect which of the visible people in a video are speaking. Here is an example.
So whether or not it matters, I think for legal reasons, it doesn't really matter whether or not you...
In this video, the man in the middle is speaking. So the system identifies he as a blue box. The other two non-speaking men are marked as red boxes. Active speaker detection can be used in the applications such as video retargeting for meetings, speaker diarization, speech enhancement. The active speaker detection can be classified as a visual-only method and the audio-visual fusion method. When the audio is not available, the mouse becomes the most important cue for detection. The most of works focus on capturing the mouse key points and determining whether it is speaking based on its motion. Without audio information, we can imagine that these methods cannot handle the non-speech face or mouse motions. On the other hand, audio-visual fusion can improve the prediction accuracy because speech rhythm and word pronunciation are closely related to facial motion and mouse shape. For example, in this work, Joseph proposed an end-to-end multimodal active speaker detection framework with a two-string convolution network for audio-visual feature extraction, followed by a recurrent neural network for classification. However, giving a stack of raw images as visual input, it's not intuitive for the network to learn the subtle differences between neighboring frames. In the literature of human visual perception, the human visual cortex contains two pathways: the ventral stream, which performs object recognition, and the dorsal stream, which recognizes motion. But existing active speaker detection methods mainly learn the visual embedding only from a stream of raw images. Therefore, we aim to advance the representative ability of the visual embedding by incorporating a motion stream. Accordingly, we can incorporate optical flow into the model to enhance the motion recognition. The dense optical flow describes the motion vectors of all pixels of the image. As this image shows, the dense optical flows has several advantages over grayscale image. First, the dense optical flow illustrates the unique motion pattern, like open and close of the speaking mouth. Second, the dense optical flow can capture the subtle motion of the textureless facial skin, like the cheek. Third, the facial generates consistent optical flow under different illuminations. Fourth, the optical flow removes the identity-related visual details, and it can avoid the network misleading the correlation between the identity and the speaking label. Based on this observation, we propose an end-to-end active speaker detection framework. The inputs are three sequences: optical flow, face image, and audio feature. Here the audio features refers to the mouth spectrogram. We concatenate visual embedding and audio embedding and feed them into the prediction network. Here prediction network is a LSTM, long short-term memory network. Audio embedding is a mobile net. The output is a binary label speaking or non-speaking. To fuse face image and audio flow, we apply two architectures of visual embedding networks: visual couple embedding and independent embedding. For the visual couple embedding, we extract the audio flow from the consecutive face images. and then stack both of the face image and audio flow together and feed them into the mobile net. The output of the last layer is a 128-dimensional visual embedding vector. For the independent embedding, we use two mobile nets with different ways to process the input face images and audio flow, respectively. The output features vectors from two embedding networks are concatenated as a visual embedding. In the implementations, we replace the last fully connected layer in the original mobile net with a global average pooling, that is a GAP layer. This is used for visualizing the class activation map, which we will discuss later. Here I list the parameters of the embedding network. For the prediction network, given each 10-frame clip, we concatenate both a visual and audio embedding to form a composite feature as the input of the prediction network. We design the prediction network based on a sequence-to-sequence model, including an encoder and a decoder. The encoder and decoder are based on a long short-term memory network with 522 units, while the decoder is followed by a two-dimensional fully connected layer and a softmax layer. The decoders produce a sequence of a prediction probability after receiving the state vector of the encoder conditioned on 50 embedded feature inputs. To train the model, we use multitask learning to improve the learning efficiency of each network. The loss function is designed from three aspects. First, minimize the visual-based classification error. Second, lens audio-visual synchronization. Third, minimize the classification error after audio-visual fusion. The final loss function is a weighted sum of these three loss functions. We use AVA active speaker dataset to evaluate our system, including 28,108 face tracks as training data and 7,900 face tracks as test data. Each face track ranges from 1 second to 10 seconds. As the right image shows, each face track includes a face region sequence and the audio signal. Each frame will be labeled as non-speaking or speaking. There are 72.5% non-speaking face frames in the dataset. We evaluated the performance using AUC, which is short for Area Under the ROC Curve. Here we list the result of the ablation study. We abbreviate the facial image, audio flow, and audio signal as F, O, and A, respectively, IE for independent embedding, VCE for visual couple embedding, CL for contrastive loss. First, Table 2 shows the performance of different features in the independent embedding network without contrastive loss. The trend demonstrates that the audio flow can provide an additional and important clue for detection. Second, we evaluate the influence of the contrastive loss. It shows that the contrastive loss can improve the prediction accuracies around 1% to 2%, which proves our assumption that the contrastive loss is beneficial to lens synchronization information between audio and the visual feature. Then, we evaluate visual embedding by comparing model between independent embedding and visual couple embedding. The result shows that visual couple embedding network can outperform the independent embedding network. This is because it can learn the spatial correlation between raw image and audio flow. To visualize the distribution of visual couple embedding and the independent embedding, we randomly select 3,800 embedding features from the test set and project them to the 2D space. The Table 4 quantifies the separability of different embedding features in terms of ratio between intraclass and interclass distance. We can see that the fusion of audio flow and face image appears to be more separable than the single modality features. Meanwhile, the view-coupled embedding performs better than the independent embedding, proving that view-coupled embedding can generate more discriminated features. This can explain why the visual embedding network can achieve more accurate classification. We also compare our best baseline with state-of-the-art method, which has the same architectures as the model, phase audio as inputs, contrastive loss as a loss function, but it's trained with an additional cross-entropy loss for an audio embedding network. As the table shows, our proposed models, phase, audio, and optical flow as inputs, view-coupled embedding with contrastive loss achieves consistent improvement over the state-of-the-art method. In addition, we evaluate the state-of-the-art method and our best model against the different phase sizes and orientations. This table shows that our proposed method consistently performs better than the baseline, even with a small phase or a set phase. These results indicate the robustness of our model in adverse conditions. To understand which part of the phase region contributes to the prediction, we visualize the class activation maps generated from the view-coupled embedding network of our best baseline. The class activation maps of speaking phases show that region with the highest response lies on the mouth region. Meanwhile, the mouth region of non-speaking phases shows lower response than the other facial regions. The results demonstrate that our model can localize the mouth region and analyze it to distinguish between active and non-active speakers. Last but not least, we prepare a demo video. In this video, we deploy our trained model to a real-time active speaker detection systems.
Hello, hello, hello. Can you hear me? Can you hear me? How are you? I'm fine, thank you. And you? Hello, 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 hello. My name. Hello, my name is Chung Huan. I like the audio speech. Can you hear me? Can you?
Hi, it's Wei. I'm from UT Dallas. I'm doing some event detection here, so it's near the deadline I'm writing